Swayam Prabha. Digital India. Educated India.
Web protocols and web software. And I think I found this reading view which seems to work within a bounded window, so I'll use that. Um, Here, the web is a I mean, in the context of protocols, the web is a pretty strange thing because it's a way to build applications together with a underlying network protocol. So it's basically a way to build distributed applications, and nothing like the web really existed before. That's one of the strange things. There were distributed applications, but they were purpose built, whereas this is like a general purpose distributed application platform. And so we will tie it together with the network protocols that we studied before, but I hope it will be clear to you that there is a much larger picture involved. And unlike the previous case where there is this nice textbook, I'm not aware actually of any good material on web application from a principled perspective. You can get, 20 gazillion how to build something with Python and those kinds of things. But what are the underlying ideas? Those are not, to my knowledge, there is no good book. I mean, if you guys know of something, tell me afterwards, and I'll be happy to. I did look up, though not recently, to see if somebody has written a decent web software principles करके book, लेकिन है नहीं, as far as I know. Okay, so in any case, this is the um, structure of web software, the overall view, which I hope all of you are aware of. So in this case, I had done this thing for NPTEL, so there are pictures are from there. So let's say you have your browser. We all know this kind of stuff. You have the website and URL and so on. And roughly what is happening every time we interact is like this, right? From the host name, you talk to the DNS, which tells you the IP address. You get the IP address back. Then you establish a TCP connection to the service, and then you send what is called a HTTP request across it. So that's the part we will do a review of, like what is the connection between TCP and HTTP and so on. And then you get a response back, which happens to be an HTML page. So these are the elements, and overall idea we use daily. Of course, I guess you guys use it lesser than we used to because there's so much mobile phone stuff. But you meaning, I mean, your generation, I would say computer science people probably use the browser more than normal people nowadays, but I don't know any good statistics on that. In any case, um, fundamental rules we know: browser is supposed to locate the server and get the relevant data, and it's the details that make the stuff strange. So let's look at it from a completely different perspective. This is not a perspective people normally think of when talking about the web, but what we will look at is what the web did to applications. So here is a command line application, and as an example of a command line application, right, I have, let's say I have this ACM school directory here, and my command line application is just ls, and maybe I have something like this, some thinking I was doing about what to do, and so I have some more and so on, right? So this is my traditional app. So what is a traditional app? A traditional app says that there is a command. So in this case, let's say I do ls of a particular thing, which is a CMSS plan, and I see something, then I give it some arguments, etc., and then I see something else. Well, um, the basic idea is command comes across, the program talks to some database file store, does some storage IO, and you get a response and you show it to the user. And what is the internal architecture? It's basically a function call that runs some computations in conjunction with the command, including this IO. And then, if there are like things like multiple commands via something like standard in or something like that, then you loop over them, etc. Right? These are all very straightforward things. And then from the point of view of the shell, CLI is literally a function call. So in the case of the shell, you can do these kinds of weird things, right? So grep dash I, let's say txt. So this is actually function composition. I mean, pipes are fundamentally the same thing as composition of functions, except in a interesting syntax. And that's like a reasonably decent starting picture of what an app is. But users think of it as a command. Now, when you put a GUI on top of this, so for example, if I do this kind of thing, right? So I have a GUI here. In this GUI, what happens? I run the app. So I'm the user. I'm running this thing. When I do things like clicking here, etc., what is happening is that there is a view which is the underlying thing presented in a prettier way, and there are these so-called events. So my mouse goes there, the event goes to this view software. Underneath, inside the view, there are what are called handler functions. Many times they talk to the model, which is a data structure that represents this list of files, and then that data structure is filled from the data store. So you run the app, show, view, button pressed or whatever, clicked, update the model, show, etc. And I can also do other things like do a new and make a new folder and so forth. Now, what is the big difference between this and the CLI is that if I want to make a new folder, I literally have to type an independent command. Whereas here, this is happening in a session sort of. It's like it knows where I am and so on. Here, the command doesn't really care or know. I mean, in this case, the mkdir and all does, but I could just as well do mkdir of somewhere else, which is I have some demo directory, and inside that I can do something like this, and it will still work. So it doesn't need as much context. It's like this independent thing on its own. Now, in the GUI, you have done this kind of separation. So think of it this way: this single blob called a program, its parts are coming apart. So we have a decomposition from view to model, whereas this whole thing was a blob called program. And then the internal architecture of the app changes. So you do these controls and widgets and whatever, and link this thing to the computation with explicit data representation. And then what is called a event loop. You listen to these events until some termination happens. So termination basically means you do this close event. Now, what the web does is it takes this decomposition and moves it on to different machines in a distributed system. So you have your user, you have your browser, you have this server, there's request response cycles as opposed to function calls, and then a database with instead of say a local file, right? So in some interesting ways, a browser is a view or a device for, or a, what shall we say, program for showing views. And a server is in a very real sense an analog of the model, where it maintains some notion of what the application is supposed to be on a different machine. So you should have this mental picture of these pieces coming apart, because the web is largely about decomposing these pieces and recombining them in very different ways compared to CLI or a GUI, which is born in a world where one person, one machine at a time, and no huge amounts of interconnectivity. So let's see. So CLIs have a function like flow, no memory across invocations. The um, and then GUIs retain some sense of history. but then there is this separation of model and view. And web programs kind of achieve this history, but they achieve this in a strange way. And we will try to uh, talk a little bit about it. I hope you know many of these things at some level or another. But even if you haven't, I want to create this picture in your head of how these ideas are all tied together. So that's our thing. And then now you begin at the other end of the web, which is to start studying URLs and the HTTP protocol, right? So we are going to look at this technically, which you may or may not have before, depending on whether you studied it or not. Even though we use it every day, you don't necessarily think of all these things very, very technically. Uh, yeah. So and then we talked about protocols, so I'll skip that. And right. So fundamentally, right, uniform resource locator. So of the form protocol hostname colon port followed by path. So if we have something like this, then we know that this much, the protocol is that and the host name is that and the path is something like this. But the main point is to the browser, it's actually a little program. It's a set of instructions which says look up a server, then use the protocol HTTP to talk with it. Because remember, the underlying thing is TCP/IP. It's not HTTP. So it's a choice to use HTTP. In fact, there used to be. We'll talk about it a little bit later. You could use FTP in a browser once upon a time, and actually like 6 months ago. So this is a very recent change. We'll talk a little bit about it. And then you send this path to a server, and then the server receives the URL and interprets it as verify that I am IIT Goa, and then you send whatever the resource is at this path back to the browser, where resource is just a pile of bytes. It's usually an HTML document, but can be PDF, images, blah blah blah. And then the path component has this technical name like request URI. Most of this stuff, of course, is on Wikipedia and all, but usually you don't have reasons to go into the technicality. Then the next kind of thing is this thing, URLs with query strings. So we'll actually do this. Let's go to this thing, and I couldn't copy from that, so I'm going to switch into this thing. So we'll go here and copy that, and I have some browser here, and I go there, and oh, I should have crap. Okay, forgot to do that. So web tools, where should I have it docked to the right? Okay. And let's take a look at the network. So I'm going to reload this Madhav Sangamagram thing. And here you can see the browser talking to the server and getting all these things. So so far so good, right? This is a vanilla URL. But now if you do this, which is you search for something like URL locator. See, as I type this, you can see the browser talking to the machine. And if I do that, then a search gets sent, a new page happens, etc. And what happened? Search URL locator. Okay, so okay, okay. So anyway, what I wanted to show you was this, that there is this part, and then you have a question mark, and then you have this so-called query string, right? So it's a basically a different format for a URL. Main point is, think of a URL as a little program actually. It's the browser is an interpreter in the same sense that you have your Python interpreter or whatever, and it follows the instructions. And then this is a different syntax for function calls basically. So the parameter names here are this search equals and title and so on. So it's also like making a function call. And then there are other peculiar things like this URL, which was a space, it turns into this plus over here. So you do these kinds of encodings. And the reason to do things like encodings is that it's difficult to I mean, when you're processing large amount of textual data, is a space intentional or not, especially for things like file names and so on, can be quite tricky to understand. And you don't want to trip yourself too much, so you come up with things like this encoding thing. And then the web is absolutely full of just weirdness on top of weirdness on top of weirdness, because unlike say operating systems or whatever, which grew up in academia and eventually remained in academia, so you can write books like principles of operating systems or principles of databases or whatever. The web grew a little bit like this biological organism, and so it has it's a agglomeration of all sorts of strange things, which may be one reason why great books don't exist. So that's the overall structure. And then you can have things like this. So one interesting thing you can play with is this example.org, right? It's like a site created by the Internet Authority. So it's this domain is for illustrative examples in documents, etc. And um, you can see this what is called the IANA, which owns this domain, and you can do things like this. So um, here now port 80 is assumed, but as you might know, you can actually do this and it will still work. Now, stupidly, browsers have decided to hide things like ports when they can. Um, well, I suppose they are trying to, be user friendly or whatever, but it's damned irritating as a programmer. In any event, you have these port numbers, and HTTP has 40, HTTPS has 443, FTP uses 20 and 21 and so on. I don't know if you know what FTP is. It's called File Transfer Protocol. I'm not sure your generation uses that anymore, but it's by the way, it was designed by an Indian guy, okay, who worked at MIT, and he did it in 1971 or something, long, long ago. It's one of the first uh, applications to work on the internet, and it's very strange internally. Like for example, it uses two ports and stuff like that. Now we regard it as a mistake. I mean, in those days, it may have made sense. So, and then you might already know this part, right? That the server's IP address is kind of like a phone number, etc. And a port number is like an extension number for somebody's office. And then the complete address has both parts. So you can run your own web server quite easily if you haven't done it already. And a simple way to do that is to actually do this thing. So Python, for example, Python 3 at any rate has a thing called HTTP server built in. Let's call it 9000. And it will say I have started this server and I can actually now do this thing localhost. What's the port number? 9000. And now it shows you the same thing. And one other interesting thing that I will, okay, I'll do that when the time comes to do that. Um, so so far this stuff you probably know, even if you didn't pay too much attention to it. There are different ways to talk to local systems, like using this kind of IP address or the name localhost. And bottom line is a URL is a program, right? As far as a browser is concerned, and they are addresses of, technically they are addresses of resources, but I mean, usually HTML and so on. There's a protocol, host name, yada yada yada, a bunch of standardized terminology. to, if you're writing web applications, all this becomes incredibly important. But to learn about what the world is like, that's why I'm, showing you that these are technical things. They are little programming languages in some sense, right? So that's the outside in picture. So if a web app is a distributed app, it uses this thing called a URL, and a URL is kind of like a application name in some sense, plus a little program with a bunch of internal structure, and all of this runs on top of the protocols. So our starting diagram here, right, we talked about this part so far, and maybe and now we'll talk a little bit about this interactivity side of things. Right. So then um, uh, you have TCP over HTTP. The layering is that there is a protocol called IP, the Internet Protocol, which establishes rules for how to identify computers, how to send packets. Then, um, uh, the very word packet says that you send these bounded messages. You don't just talk for a while and stop. It's like you send this block across. And the curious thing about the internet is, in principle, every packet can take a different route, because if some route failed, then the system is capable of dynamically rearranging itself so that somehow you can reach the other side. And there was it was a kind of a theoretical breakthrough again, to be able to think of the network like this, because when all this stuff was invented in the 50s and 60s, the dominant network was the telephone system, and telephone system is fundamentally the landline system, right? It's fundamentally literally a physical circuit. So there's literally a wire stretching from your home to somebody else's home via these intermediate hops. So everybody was programmed to think in terms of continuous circuits, and these guys, Paul Baran and somebody else, they invented this idea. So then you got your datagram network, and on top of the datagram network, you establish a connection. So you think of, we are talking, right? So there is a connection, and everything I'm saying is getting packed up into these packets and coming to you, and so on. And the entire set of packets constitutes a single ordered conversation. I should say a single ordered conversation, because just like we talked about this flow control and reordering before, the ordering matters. And then now, what do we mean by layering? So we'll take a look a little bit more in detail, but fundamentally, think of this analogy, right? So every human speaker uses sound waves, and they have some shape, but then you hear it as a particular language. So the sound waves and your ear mechanism is the TCP layer, and on top of that we have some structural layer of English or what have you, and that's kind of what is happening. So TCP is the underlying thing that just transmits some bytes, and then HTTP is a language structure, linguistic structure that sits on top. So then, relative to HTTP, TCP is a low-level protocol, and relative to TCP, IP is a low-level protocol. So then every HTTP client sends TCP messages in this format, and depending on how much time we have, we'll take a look at some of these things at least. And then as long as you get the formatting right, TCP stream is considered HTTP. It's not like there is a thing called HTTP. It's an understanding. It's an agreement between the server and the client that the syntax they will use is will be called HTTP. So again, right, we come to that analogy between protocols and programming languages. So HTTP, the protocol in this sense, is a programming language. So you see how many times I have been saying this is a program, that is a program. URL is a program, HTTP is a programming language itself. These ideas are like they pervade the space of thinking, but we don't, I guess, normally are not very aware of that. So I hope from this session you carry away that message. Right. So then that's protocol layering. So more metaphors and analogies. HTTP or HTTP over TCP is like two human languages. TCP in this metaphor is the biological mouth ear mechanism. HTTP, FTP, and SMTP for email are like Sanskrit and Marathi. And clients and servers must both agree to speak a language. And a FTP client cannot interact with a HTTP server, although both are layered over TCP, same language thing. But then browsers are, I mean, they still are, but they used to be more than that. They used to be these multilingual devices. Like I said, FTP was supported until 6 months ago. So I used to show this example that you could go to this HENet site and you could either go to it via HTTP or you could go to it via FTP. But like I said, that just stopped working. So now only this thing works. And the browsers, what they did is they removed FTP because it's getting less and less used, and browsers have a huge security problem. So now this is what they do. They'll ask you to pick an app and do something. But once upon a time, they used to internally manage and show this similar content via a different protocol. And that was like a very cute, nice teaching demo, which the browser makers uh, I mean, now I can't use it anymore, except, you can do this kind of thing. So there's only one remaining thing that browsers have, that is like this. So I have this, and I have, see, this HCMSS, etc. So this is, that thing we had discussed, right? The structure here. So we have this GUI, and technically I'm seeing the same thing, but this time I'm doing this circus of going through this request response protocol, even though of course it's just my local machine which is acting as a server. And the browser is, so because there's no, I mean, the operating system which shows you the file, the directory content, does not talk HTTP. So how is it that a browser can show it? The answer is that internally the browser is interpreting this so-called file protocol, right? Converting it to the operating system IO, and then whatever, I mean, what the operating system gives is basically, as we know, the operating system gives you things that look like this, right? You do ls and yada yada. So here it just takes that and wraps it in HTML. So, and in fact, if you do view source, this is really crazy. I wish they actually wrapped it in HTML. They have some weird representation. Instead, here if I go do Control U, then now of course this is HTML. If I was designing a browser, I would, but maybe this is very ancient code too. So I would have preferred not to create yet another new thing and instead just make this look like HTML. But anyway, so that's what I mean by multilingual, right? The browser can choose to hide that it looks like HTTP to you, but it ain't really HTTP. So the point of all this chitter chatter is that um, so in principle, the browser could do this for whatever protocol it wanted to talk to. But then what happens is that our experience of the web, see, if things like file protocol and all go away someday, suppose, then the browser will be a pure HTTP device. But up until then, it's this multilingual thing. And our experience of the web, especially as programmers, is this complex interaction between servers and browsers and the protocol together. There are tons and tons of options like this. So one of my other examples used to be this protocol like Gopher. There's a protocol called Gopher, um, which again used to be supported in browsers long ago, but it died probably 10, 15 years, maybe 10 years back. Uh, and FTP died like 6 months ago. So from the browsers perspective, I mean, FTP is still doing fine. So yeah. So when you're doing web development, you need to understand. So that's why I began at that application layer, right? Because you need to have this picture that there is this underlying application and stuff is scattered everywhere. Some responsibilities are in the browser, some are in the server, some are in the protocol, and so on. And you really get these. I mean, I guess the nastiness of the bugs is going down over time because these so many variations don't exist anymore. But my God, there used to be some really absurd bugs when doing web dev. So, and there probably still are. Distributed systems are a pain in the neck. Useful things, but damned annoying. So, um, and I mean, DNS, I'm not going to say very much, right? Basically, job done by DNS is to give the address. You can either have 32-bit or 64-bit, etc., etc. And after DNS helps you find the address, then TCP rings up the other computer, establishes a connection. And then once connection is set up, you can exchange the messages. So, so we are here and talked a little bit about the connection between these guys. So let's take a look at what this looks like. By the way, you get into the habit of using these tools, right? So here, for instance, I have NSLOOKUP. And if I use NSLOOKUP to look at this fellow, nptel.sc.in, what this is saying is, so this stuff is my local internal, the 192 is the local addresses. And here it says that, okay, so nptel looks like that. Is it still okay? So some remapping of addresses has happened, looks like. Uh, Sometimes when you execute this, I used to get something changed, I suppose. So, right, then we'll try this one, httpd.apache.org. So we have nslookup httpd dot. By the way, this is your internal home router, and I think I know why it's showing unknown. But yeah, but again, now you got this thing. This fellow is a IPv6 address. The others are IPv4 addresses. And here is the unpacked version of this layering business. Let's take a look at that. So this outer envelope is the IP packet, which is the lowest level. It contains a destination address. It contains a source address. I'm showing IPv4 um, instead of v6, but I mean change the numbers for 64-bit IP. So and what is header? So layering is when a message, when see, what is a message? We looked at it before, right? It's a sequence of bits which you have assembled into bytes, which you think of as meaningful. And so when you first get that as a server, when you first get that message, you need a thing that identifies that this is what this message is about. And so um, that part is called the header, right? Because it arrives at the head earlier. And it's kind of like an address on a physical envelope versus envelope content. So that's the metaphor here. And so as far as IP is concerned, uh, this is the header which the protocol itself understands. It treats everything after the header as data as far as IP is concerned. But then TCP is layered on top of that. So then After IP packets are done, the data is a TCP packet, and then TCP packets are these kinds of things. They identify port numbers, source port, destination port, and remember we talked about sequence numbering and windows and all that. So this is the sequence number and this is the so-called acknowledgement number. Those are the things we talked about in the protocol discussion earlier. And then so you have these sequence numbers for data streams, and then in turn, right, TCP treats HTML as its data, same kind of thing. So that's what layering amounts to. So address number one of the envelope, inside this envelope there's another envelope, inside that there is another envelope, inside that there is another envelope which is the HTML data. And HTTP headers identify these kinds of things, and there's no bits here anymore, right? The world of bits ends at IP and TCP, and HTTP is a so-called text protocol. That's largely for simplicity. Plus also there is this other thing that um, usually the size of HTML data is way larger than the headers, and so the idea is that you can afford to, I suppose, waste some of it. Although modern implementations of HTTP have uh, gotten incredibly sophisticated. So this is true and not true at the same time. Meaning the old stuff will still work. The new stuff will treat this in various complicated ways. But then HTTP headers contain again, uh, just text, and the body is HTML data. And now let's take a look at this. So do I have time for a quick demo? I guess, yeah, 12:07. Okay. So we'll do this. So I'll show you this example. You should play with it. SOCAT is a program that just talks TCP, and it can act either as a listener and receive messages. So SOCAT helps you write simple servers like this. So I have this fellow here. I'll kill this Python server, and let's say I do I have okay. So this is the client, and now let me see if I have typed SOCAT. Okay, ठीक So this line. So here SOCAT is going to listen on TCP port 8001, and on this side it's going to uh, act as a client. And now let me show you. I think I had this. Yeah. So in a terminal you create a client that says hello to the server, and here you have something that waits, and then it just receives that one line and terminates. So let me start my server here. So now our server has started. The only thing the server will do is it will echo goodbye. So what SOCAT is doing is it's taking this stuff from standard input, and its job is to listen like that. And if somebody contacts it, then it just sends goodbye. That's it. But it also takes the string from the other side and prints it. So let me bring that guy up. Okay, so let's see what happens. So here I have echo hello. So there we go. So the hello came over here and the goodbye came over here. And that's it. So that's like your quick one-line server. And then you can do the same kind of thing here. So for example, I have so I have this little one line, right? This is actually a entire HTTP server. All it does is say hello client server here on such and such date. So I have started my server, and now I can actually talk to it from this browser. So what port did I start it on? 8090. So let's see, localhost 8090 there. So we got it. So our server replied. And as far as this guy is concerned, it's um, just another HTTP server. So let's look at the dev tools and go to the network, and we'll visit. So on the server side, by the way, so I got two requests, one for just slash, and another for this fav icon, which is a request that this thing makes to get those little, these icon thingies, this Firefox and this index and whatnot. So let's visit it again. And so as you can see, there is a, it makes this get request, and this is the a tool you should be familiar with. So uh, no, not HTML. Shit, I forgot how to. Okay, there. So this is what is happening underneath. It's literally sending a string, a set of strings here, like this HTTP, and I'll actually do it for you. So and then it got this response back. So let me just do that. And this one we need. mm, by the way, so see that interaction is happening, because see, as long as it is speaking, what it thinks of is this HTTP protocol, the browser is happy with it. That's the idea. And to see what is happening in greater detail, we can do curl, so which is another, by the way, commonly used tool. I have mentioned all these in the slideshow, so those of you who want to play with this stuff can do that. And so I have localhost colon, what was it, 8090. Yeah, so it just talk to this guy, and it's saying all these things. So it sent this, it literally sent these strings. It said get HTTP host user agent, etc., etc. And then our SOCAT server doesn't care. Anybody connects to it for any reason, it simply replies with uh, this thing: hello client, no server. Because I mean, it's a one-liner server. What do you expect? To make this be a bit better, we can do the Python 3 thing, minus m http server 8888. So now this one is a real Python, is a real HTTP server. So I have localhost colon 8888. And if I do that, so there we go. So basically it's, if you say slash, it just serves the contents of the local directory, and this is what you send. And by the way, you can actually literally type this in. So let me see if I can type it in. So we'll use SOCAT as a client now. So I'm going to talk TCP localhost. Yeah, you should look at it in the recording if you're not familiar with fiddling around with things like this. So I'm literally typing a text, right? So HTTP dash 1.1 is localhost colon 8888, and let me say there's something about connection closing or something. What, I think it's in my slide deck somewhere. I guess not. Anyway, so it probably won't matter for this server. The exact details are there if you on various websites and all. Connect. I think I have to say something like connection close, some such thing. Anyway, it was happy by receiving just these two lines. Actually, it would have dropped the connection anyway. So it literally sent these bytes to this guy, and it did whatever it's supposed to do by default. So that's how simple HTTP really is, and that's why it succeeded as well as it did. And what all this does is, I mean, maybe I'll add something more to the slide deck to explain what this thing does. all I want to give you is a sense that simple text messages are getting exchanged, and as a result all this stuff is working. And I showed you some glimpse of curl and Firefox web dev tools and things like that, but of course our time today is pretty limited, and so I will skip over this stuff. Yeah, so this dev tools demo, you can do all sorts of cool things with this thing. So let's take a look at what all happens when you talk to something like httpd.apache.org. Actually, you know what, I want to see something utterly horrifying. um, should I do that? Wait a minute. I'll start a private window so it doesn't clutter up my Okay, so by the way, uh, you might not be aware. So people talk about all this loss of privacy and all that, but they have no freaking clue just how bad things are. So I'll show you a thing that I hope satisfies you. I think E-Sakal is like a Marathi newspaper. So look at just how many damned messages, this ad, that ad, ye domain, wo domain. It just isn't bloody ending. It's like 130 whatever requests, most of which are going to some crappy advertising thing or the other. Yeah, there. Static double click Google ads, yada yada yada. Uh, tracking. See? So once you start looking at this stuff, you will absolutely horrify yourselves. Like, first of all, these are badly written. Like, you shouldn't need so many bazillion requests to show some stupid web page, but that's okay. Getting good quality programmers is completely non-trivial, and then they have to make money, so all this crap goes on. And actually it's not as bad as I thought. The American sites are truly terrifying. They absolutely spray. I mean, Facebook probably knows more about you than you can even imagine. So anyway, so that's what happens when you get aware of how horrifying things are as far as tracking people is concerned. Anyhow, so that's the world of the web. Now let's take a look at one small part of this. Now that I have given you some sense of overview of this thing, let's talk about one narrow thing which matters for designing systems for the web. HTTP is what we say is a stateless protocol. That is, as far as the server is concerned, as far as the protocol is concerned. What is a protocol? Protocol is a rule for exchanging messages. So then um, every request to the server by the browser is independent. There's nothing to link one request to another. But TCP is stateful, because if you want to maintain a connection, you have to say, I am sending you a packet for this connection. Because I could have another connection and send another stream of packets between the same two machines, but they are conceptually independent. On the other hand, state is necessary, because you need to do things like shopping carts. One shopper's cart should not be paid for by another shopper. So which means that shopper session, the sequence of packets getting exchanged, should be distinguished from sequence of packets for another person. And so you can think of state as the current result of a specific historical sequence of events. And because nothing is built in into the protocol to say I'm talking about this particular sequence of events, you end up doing something. I mean, the necessity is to build. Um, So what we need to do is actually do something like this. So this is what it looks like inside a server, right? A server is sort of like a mini operating system. And the one I'm showing you happens to be the Java servlet thing, but it doesn't matter. Now we are looking inside the server box. And what you see is, as far as the browser is concerned, is a single user. So you talk to this server event loop. And in response to the browser and the user and so on, you get these things called servlets, which are sort of miniature operating system processes running inside a server. And the idea is that there is a servlet which is acting on your behalf, because there are billion other users, and each of them has a little servlet of their own. So the trick is to use a common piece of data as a common key that links URLs issued by a single browser to a single site. And so the protocol then was changed to add a header called a cookie. That's where that whole cookie thing comes from. A header to set a key and a header to carry the key. But aside from a standardized meaning of the word cookie, the protocol does nothing whatever with cookies. It's the client's responsibility to make sure to send the cookie to identify uh, causal connections between requests. HTTP, the protocol, says nothing whatever other than providing a little carrier. So then here is what happens. So you have a browser, sends the initial request. On the response, there is a header which says set cookie. Then the browser says that, okay, if you have asked me to set a cookie, then for this entire domain, whenever I talk to the server, I'm going to send this whatever data you ask me to send, and it will continue throughout the HTTP request. So that's how HTTP, which is stateless, recovers the higher order thing. And so um, server can tell a browser how long to remember, but browser can delete cookies at will. So again, it's like an agreement. If the browser throws away a cookie, it's gone. So that's what it means to log out of a website, right? When I mean, log out just means the browser destroys its own cookies. Otherwise, there's no logging in or logging out precisely. So all these kinds of things are done using cookies. And so let's take a look at what we talked about, right? We said you have this distributed application, you have a layered set of protocols for talking to each other. And then that there's some additional data you need to carry to connect the different requests. And finally, to conclude, this whole architecture of the browser talking to the server, getting some resource back, maintaining this extra data like a cookie and so on. What we say here is that the state of the application, so you have put some data into your shopping cart or whatever, and the server is going to remember it. It's saying, together with your account and the current cookie and all, here is here is the associated data. But then at some level, you get on the browser a prettier representation of what the server actually has. So to go back to our file example, this data, which is a list of all these things, is actually a resource which the server, I mean, in this case it's fake, but okay, maybe let's take a look at a better. So in this case, this is a resource, and some version of this resource has been sent to me. And for example, let's say I have this install thing here, right? The server meanwhile could have changed it, so maybe this will no longer be meaningful, but I don't know that, because in a distributed system you can't know that until you actually try to use the information. So this gap between uh, the state on the server and the state on the browser, the terminology used to talk about it is called representation state transfer. So read it backwards: transfer of a representation of some state on the browser. So maybe I should just write that down, because representation state transfer, a representation of the state as maintained on the server is transferred to the browser. And so everything that we need to interact with the application is contained in the browser page. This has interesting consequences. Here is one of the most interesting ones. You do not need a separate browser to talk to a bank versus to talk to. There is something really, really peculiar about this, because prior to the invention of the web, you needed, if you wanted to talk to your bank versus to your Flipkart or whatever, you needed a separate program. And in some ways, the mobile platforms have brought this world back, but it isn't quite so hideous as it used to be, because the web has taught designers what a great design looks like. So the apps are actually a lot like each other, in part because they are also designed to work with the web at the same time. So the web bought a certain uh, aesthetics and a certain logic and a certain um, uh, I suppose, I mean, it's like you have no reason to experience a worse world anymore, but boy have we experienced it, right? I mean, programs used to be mind-blowingly hideous, and they probably still are, desktop ones. But the apps and the web programs are actually like beautiful, and they pay attention to what you. Okay. You want to see an example of a horrible program? Go to any government site. Basically, I mean, the Covin app is actually not that bad, and the website is not that bad, which is a good thing. But otherwise, you go to your state government sites and it's just a freaking horror show. I mean, even given a good model like the web and how to design a app, you will get these you know uh, cheap programmers with probably a lot of bribery and whatnot, and substandard work. And I mean, the web with its improvements allows these people to do horrible programs. Without the web, it would have been an even worse disaster. So to calibrate, how horrible things can be for you, that's my story. And so that's our little capsule of how to tie together applications and the protocols and the philosophy, so to speak. So that's it. You guys sound a little, I mean, well, I can imagine you are stunned because we went through a complicated journey in a very short period of time. But it really is the, I mean, maybe you can watch the recording again or something.
Excuse me, sir.
हाँ बोलो.
So do we have these different architecture, like
Different
different
what?
protocols?
Huh.
So these are only for just for reliable and secure connections, right? Secure to do everything in reliable and secure manner, right? So we introduce
Uh,
different protocols just to make sure that these are all secured and reliable, and we have transferred our data correctly and everything.
yeah, see, remember in the morning we talked about your bottom line is electrical signals. On top of electrical signals, you have constructed this huge set of abstractions. First, you change the electrical signal into bits, then you change it into bytes, then you change it into, all these network layers and this and that, and all the way to the top of the application stack. All of it is possible because in every layer, we have managed to get correctness, we have managed to get efficiency, and we have managed to get these design principles that involve all this hierarchical thinking. So
Yes, sir. So in this efficiency word, we have efficiency means our data is transferred correctly, right?
no, I mean efficiency, I mean correctness is correctness and efficiency is efficiency.
Like
They
we have
interact
increased
with each other.
performance time by time using changing these different protocols architecture.
Okay, okay. Yeah, I mean, usually you first get the protocol correct. And then once you know you have a correct protocol, you can work on creating more efficient version. So in this context, what efficiency means. So for example, right now there is some work going on, I think, or maybe it has been finalized, like the new version of the HTTP protocol, right? So you saw in that e-Sakar thing that there are all these 130 requests getting made and probably more which are hidden by the JavaScript and all to just get a little newspaper page on my system. Now, in the old days, this would have been impossible, right? 130 requests would have meant it will take forever to show the page. Now, where
Yes,
did
sir.
the
But for
go ahead, go ahead.
yes, sir. So yeah, you were telling that. Okay. Yeah. Okay.
So now what happened is that efficiency was looked at all layers, right? The hardware got faster. People figured out better ways to package the data. And the latest edition of HTTP, for example, even though they look like independent requests, they are usually packed together and sent in one block. That is one of the achievements of the latest versions of HTTP. And browsers are absurdly complicated systems by now, especially when they implement these convoluted protocols like HTTP 1.2 and all. And all that is in the aid of efficiency. And here efficiency means responsiveness to users, right? It's not about bytes and bits or whatever, because see, if you could see the website in 10 seconds, why do you care how slow the underlying system is? You have no interest. You are only interested in the top level perspective. How much time does it take for
Yes,
me to
sir.
read what
But
I
how we improve this from 10 seconds to 5 seconds actually?
it's improvements on like I said, all the entire chain, right? Hardware, software, better methods of making connections, congestion control. So congestion control, for example, is essentially what you experience when you drive on the road, right? That
Yes.
if you had better methods of making the journey and better controlling the traffic, there are two senses of efficiency. One is, did the average time experienced per person go down, or in the same amount of time did the number of people reaching from place A to place B increase? So from the point of view of the overall system, it may be important to get a large number of people from place A to place B, but from your perspective, you want to get as fast from A to B as possible. You don't really care about what happens to the other people. So balancing some these things, a lot of work was done at every layer of the stack, right from the hardware with its electrical signals to the software at the top. So there's no one place where efficiency comes from.
Okay, sir. But as we discussed in our, like, we have protocols, we have acknowledgement bit, which is the
Yes.
check that if the data is received and all these things. Here, if we
Yeah.
change some things, like if we introduce some new architecture where we do other amazing things, so can we increase efficiency from this aspect?
Yeah, I mean, that's the example I gave to you of this slow start in TCP, right? That was considered a major invention back in like 1986 or 7 or whatever. By now, I'm sure there are many of them like this. The place to go to look for that is a conference called SIGCOM, SIGCOMM. That's where all the
Okay, sir.
network performance researchers meet.
Okay.
Yeah,
Okay, sir. Yes, sir. Thank you, sir.
sure. Yeah, play with these tools like SOCAT and all. Okay, they are a lot of fun. Um, NS lookup and all that. I'll add some more slides to it in case you want to do that. Write
Yes,
your
sir.
own little
One more.
SOCAT. Sorry.
Yes, sir. I have one more question. Sorry
हाँ
for
बोलो.
interrupting. Yes, sir. So, as we just discussed, like this efficiency part is at all the levels. So, it- just can you give a example, like what is the difference between introducing this? First, we have 2G, and then we have 3G, then 4G and 5G. So, what
Ah,
are the differences we have in all these things? So,
ah.
where we are
So
changing all these things so that we are getting faster and we are getting more efficient.
Okay. No, so the 2G, 3G, 4G is a pure hardware and the low level software world. So I think the meaning of things like 4G, I haven't looked at it in a while, but the last time I looked many years ago, what I remember was there were some mathematical breakthroughs which made it possible to use the available electromagnetic spectrum much better. So in some sense, the breakthrough happened at the level of maths, not really at the level of hardware or software. So the software which followed the maths then delivered better results.
Okay, sir. So means we are at this, we are using the same protocols and everything, but at the
Yeah,
mathematical level and the hardware level of our, like, doing the computation, we have just
correct.
increased our performance, like introduce some new mathematical model which can uh,
Huh.
use more electromagnetic spectrum.
Correct. Basically, and use the spectrum far better than we were able to before. See, the problem with the electromagnetic spectrum generally is that if two people are trying to use the same spectrum, they interfere, and so most of the mathematics is clever ways to deal with the interference.
Amod, may I add? Ashish here.
Yeah, yeah. Go ahead.
Okay, so to answer his question, just 1 minute. I will close this call. मेरा कॉलवर है कॉल करते तुम हाँ okay. Sorry, Murphy's law. So, uh, like it started with 1G, and that was what it used. If you would know frequency modulation (FM), so at that time it was like analog data which was being put. So it was just like no security, nothing. So the amps, as you can go through the history of mobile communication, amps which was made in US, and there was a similar thing in Europe. So they simply use the same technique as what we use in the FM radio station or something, with no privacy, nothing. But 2G is the first time when it was like the data was represented. I mean, it was like what you speak. Analog data was converted into digital data, and it was packets that were sent. And as Amod said, there is the constant research goes on how to represent or how to pack in more and more data. And most important thing is it should be receivable at the other side, because most of the time you see that the voice is not good or your signal strength is not good. And the key issue lies here in case of the difference between wired communication and wireless communication is that wireless is a shared medium. There is no way you can have two people using the same frequency band and using it at the same time. Many can listen, but only one can talk at a time. Whereas in a wired communication, if you are falling short of bandwidth, you can easily lay one more cable next to it and your bandwidth becomes double. One more cable, it becomes 3 times. That luxury doesn't exist in wireless communication because your spectrum is limited, and there is no way you can invent more spectrum. So you will find that that's why one of the reasons why spectrum sale and all those things, I'm not sure whether you were, how old were you when that issue came up in Manmohan Singh's government, that they were accused of not giving it in a fair manner. So that is the most precious commodity today, and people are willing to pay crores of rupees, hundreds of crores of rupees to own that spectrum, because the key to that lies in owning the spectrum, because that is where the key thing comes in. And as Amod said, it was the mathematics like QAM, and there are so many modulation scheme, and a mix of that, which resulted in having more data being packed in, and then again compression of voice. And there is one more aspect that comes in, that is speech reconstruction. That is, human brain is able to reconstruct the spectrum, I mean the received voice, in such a way, even if some packets or some things are dropped in between. So all these things, mathematics plus the physics of electromagnetism plus the ability to recover data which has been transmitted uh, with a some kind of interference that is coming in, like you turn off your monitor or turn it off, some electromagnetic waves are generated. So wherever there is a dv by dt, a high dv by dt, due to a high voltage or a low time, that is high frequency, that is a cause of concern. But the mathematicians have been able to figure out the ways of removing such external interferences to the extent possible. Uh, by the same token, if you have a jammer or something like that, which is a very high intensity spurious signal, then obviously your signal is going to not receive.
Okay,
It is, of course, the entire stack gets changed, but the stack gets changed because the lower layer changes. So to take advantage of what lower layer offers, or to overcome the limitations of the lower layer, physical layer, you incorporate certain features in the layers just above that, and make sure that your applications continue. So at some level you have IP, voice over IP. So IP is an established protocol. So those layers, anything above that is not going to change, as long as the lower layer continues to offer the same facilities and overcomes the issues that it faces. The upper layers will remain same. Over to you, Amod. Sorry for that long intervention.
Yeah, no, it's yeah. I mean the
yes, sir,
layering
it was
is,
good, sir.
yeah, the layering is all over the place. It's like it plays a role to enable you to separately evolve all these things. So among
Yes,
other
sir.
mathematical breakthroughs, there are things called spread spectrum communication and these wavelet transforms and all sorts of strange things. They're quite miraculous actually. But
Okay, sir. Yes, sir. I got it. Thank you, sir.
yeah, so bizarrely enough, spread spectrum does anyway. Sorry, somebody else with a different question, because yeah, this thing can go on for a long time. So
Sure, sure. Thank you, sir, for your explanation. It was
sure.
very good.
Yeah, hi.
Hi.
I had a different question. So, I was reading up a bit more on software-defined networking. So, it would
Mhm.
be nice to know your perspective on how and I mean, why do we need software-defined networking, and how is it going to kick in?
See, you want to do software everything. Why? Because it's soft, right? It can be reprogrammed. So I mean, hardware is basically just crystallized software. You put something in hardware, but in, I mean, I don't know if you have seen how VLSI and all these chips are designed. They are themselves programs in some sense. So whenever the adjective software defined is added to something, it just means that somebody comes up with clever ways to make something changeable. That's pretty much it as a general perspective. So software defined radio, for example, or is essentially ability to do strange things like I guess I don't know if software defined radio actually does this, but I could imagine, for example, Ashish was talking about this switch from 2G to 3G or whatever. So basically, if you could do software defined this and that, you could say that distribute new software, and all of a sudden, without any change to the hardware, you went from 2G to 3G or what have you, which isn't as easy if you have to redistribute hardware. So that's all it is. I mean, there is a you should look up an article called "Software is Eating the World." This was written in like 2012 or something long ago. It at that time it basically said that software is coming to dominate absolutely every part of our life, and there is no reason to think it will stop, right? It will just hardware will become more and more and more programmable, and software and all its opportunities and dangers will keep spreading. So
Yeah, that makes sense. No, I was wondering on like what exact. So as you said, HTTP is a stateless protocol, and I've also read that some tech companies are trying to now design new protocols which overcome some limitations of HTTP, but they also want to bake in, let's say, they also want to bake in their profit mechanisms into the protocol itself, right? So, uh, yeah, I was just wondering, like, how is this evolution going to shape in the next coming years? Uh,
hey,
SDN.
there is no, I mean, you can't really bake in profit mechanisms and all. I mean, if you read the popular press, they, okay, I'll give you a different example of, okay, let me give you a completely different example. So I'll give you two examples. First example is, this is important for all Indian people, right? Remember that once upon a time, a company ruled our country. You should never forget that. Companies are incredibly dangerous inventions. And I mean, that doesn't, I mean, that I'm not ranting about companies because they are also great things. But at the same time, they are also dangerous things because, among other things, a company allows a bunch of people to um, act as a unit for a very long period of time and do all sorts of shenanigans to you know for whoever the owners of the company or the drivers of the company are. So the East India Company should always be a fundamental concern, that you don't want those things to arise again. Now, um, that said, the second example is another such thing about, in the mid 90s, Microsoft was such a dominant player that once they destroyed all the other web browsers in terms of market share, they thought that they were going to, I mean, they actually fired the team that developed the Internet Explorer. They reduced their numbers by a stunning amount because the idea was, this is done. Then what happened is, Firefox, meanwhile, Mozilla, which had died as a company, but just in their death, they open sourced Mozilla. And then a bunch of volunteers, right, literally volunteers, who were previous Mozilla people, got together and built it and built it and built it. And one young kid, like 16 years, usually there is always these 16, 17-year-old kids who, given leverage like this, they change the world. So he just worked like crazy on Mozilla for 2 years or whatever while he was living with his parents or something. Blake something, I forgot. And basically made Mozilla stabler and faster. And that became Firefox. And then Firefox was such a victory that Microsoft was sort of forced to uh, restart their work, and they never really succeeded after that. But now there are new dangers, right? So the new danger is that Chrome is now open source and has always been, but then it's now getting adopted by Microsoft, the underlying engine. This is dangerous for us because, and you guys can take a lead on this actually. This is dangerous because when you, although Chrome is technically open source, when a variant of an important piece of technology like the browser dies out, suppose Firefox dies out, then the next time, where will the kid come from who solves the next crazy problem, right? It is important to have, it is important to support diversity within our infrastructure software. So you guys, even if you like Chrome right now, let's say, you should make an effort to use Firefox. If nothing else, then it will, and spread it amongst your friends and your family because it's damn good. But it makes sure that there is an alternative to Google. Then Google won't be able to do the kind of nonsense you are talking about, which is make changes to HTTP, which are important for them, because an entire community is there to fight back. So the East India Company is the paradigmatic example of uh, horrible behavior by companies. And of course, compared to that, this is like not even trivial, right? It's absurd to talk about those two things in the same conversation in some sense, but the spirit remains the same. I mean, maybe the scale is trivial, but the spirit is the same. So I would highly encourage you guys to make sure that you keep Firefox alive, because it's really your generation. I mean, our generation, some of us know this and we try to keep it alive. But if you guys adopt it and spread it amongst your friends, even on mobiles, then you will make sure that there are limits to the powers of companies. So that's the really big picture worldview of computer science, right? Because software is eating the world. So freedom of software is a crucial thing. It is utterly non-trivial.
Yeah, that's a great example. Thank you. There was one more question. So in the sound waves example, right? You give the
Mhm.
example that TCP is the medium and the mouth and the ear mechanism. So what is IP in that analogy?
Oh, I mean, that analogy works at any one pair of layers. Uh, IP, I mean, technically speaking, let's see. Okay, so okay, so the analogy is like this then. IP is individual phonemes out of my mouth, right? The thing that delivers individual elements of words. And TCP is the mechanism that says, you know, if I say a sentence like, now our class is beginning, then that is establishing a TCP connection, if you will, right? And the stream of words would constitute TCP in that case.
Okay, thank you.
Yeah. By the way, learn to think in analogies. They are nice for anchoring abstract technological things in your daily human experience. But you have to know where the analogy ends and creatively play with it.